Okay, so we're going to continue now on this video, and we're going to wind up looking at the second half of the handout, which gets into this idea of linear approximation and this idea of a differential. Okay. All right, so we're going to do this by primarily making sure we understand how to use the formula. But the big idea of this is very simple. The big idea is very simple. What it's saying is no matter what your function looks like, okay, no matter how messy it is, think about it being on a graphing calculator. If you zoom in enough, so if we take a picture of it just like right here, okay, or right there, if we zoom in on a specific section, it's going to be approximately linear. So any function, no matter how messy it is, if you kind of think about how it's basically linear at over a small interval, then we can use this idea of linear approximation to find the value of the actual function. We use a line to find a value of the actual function. Okay, so let me try to get you to look at this picture to see it. So you see in this picture here, the actual function is this. Okay, that's the real function. But then if we're trying to get an approximation of the value of the function at this spot right here, what we could think is that the tangent line to the curve at that spot would approximate or allow us to get the value of the function right there. And as long as we're not going to go too far away from that, as long as we don't go too far away, see if we go all the way over, if we move this far, okay, where the point we're actually looking at is over here, then there is a little bit of a difference. See that little bit of a difference between the actual value of the function, which would be here. Here's where the actual point is. So the actual value of the function at x would be here. But if we use the line to estimate it, we would be there. So there will be a little bit of an error, a little bit of a difference because we've moved away from this point right here. But that's the idea, to evaluate or to approximate the value of the function at a spot. What you could do is you could use the tangent line to the curve at a spot, and that would give you the exact value if you were right there. And then if you move a little bit away from that on your regular function, the line is still a pretty good approximation for it, but you just can't allow yourself to get too far away because the amount of error, the difference here, would get bigger and bigger and bigger. Okay, and one of the things that can really affect the amount of error that you get when you use a linear approximation is concavity. So that's what this is looking at. Affects the amount of the error, how far off you would be from the actual measurement. So do you see, like if you were dealing with a function, this function f, and you're using this line, okay, right at A, you'd be right on target. The values would be the same. But if you move down to here and you use the line to approximate the value, that would be the amount of your error. Okay, or if you move this way to some point away from A, this would be the difference between the value you would get using the line and the value you would get using the regular function. So the error would get bad pretty fast, wouldn't it? Okay. And notice that the line is always above the values of the function. So that's why it says the linear estimate is going to be an overestimate. It's going to be bigger than it should have been. And then you can see here, this is the reverse of it. So here's the line we might use to make our approximations. If we're right at that point A, the value of the function at A and the value of the line at A would be the same. But if we move to here, there's going to be this much error between the two. Or if we move over to here, see the difference we would have between the two. And the further we move from A, the worse our approximation would be. And because this function is concave up, see how the linear approximation would be an underestimate, because it's always lower than what it should have been because of the concavity. That basically is the big idea, that we can use a line to approximate the value of a function. Okay, but be aware that you want to be close. You want to stay close to this point of tangency that you're using when you write the linear function. Okay, so let's look at an example. So we're going to look at example 2. Okay, so with this one, it says find the linear approximation to this square root function at x equal 1. So that means that part right there means trying to come up with, that means we're going to try to come up with the equation of the line tangent to this at x equal 1. And that line would be the equation of the tangent line. So you've done that sort of thing before. So that's kind of what you're doing here. Okay. All right, so this formula is really just the equation of the tangent line. It's just in a, they're doing a little more of the work for you. It's not how we calculated the tangent line, but that's what it really is. I'm going to show you that. So like when we did the tangent line, do you remember what we did? If we wanted to know the equation of the tangent line to a curve at some point, x equal 1, some x value, x equal 1, what we did is we plugged 1 in to the function to find the y value. And it just happens to be 1. So the ordered pair is really 1, 1. Then we did the derivative of the function to get the slope. And so since that's x to the 1/2, it would be 1/2 x to the negative 1/2. And we want the slope at 1. So we find the value of that at 1. And remember, x to the negative 1/2 is really 1 over the square root of x. So we're going to put a 1 right there. So that'll be 1/2. And then what we did was we used the point slope formula. And the x coordinate and the y coordinate were both 1, so it would look like that. And then we would move this to the other side and also distribute. Okay. All right, so really right here is where I want you to see it. So we're trying to write the equation of the tangent line. Right, so that's like the L of x. So this is the L of x. Okay, so L of x minus the y coordinate of the original function at that specific point. Okay, so that's this. That was the a value equaled the slope, and the slope was the derivative of the function at that specific spot. And then this is x minus the a value we had, which was 1. So you see, it really turns out to be just the point slope formula rearranged. Okay, let me do it in general. So the slope formula rearranged. So you'd really have had y minus f of a equals the slope times x minus a. Okay. And then when you add that f of a over, you'd get f of a plus f prime of a times x minus a. It's just the point slope formula, really camouflaged. Okay, so that's just looking for the tangent line to the curve at a particular spot. All right, so we're not going to really do it that way. Okay, the way you would do it is like this. Let me get myself a little room here. Now that you have that, and it's a take-home test, you have the formula, you can just use it. So to get the linear approximation, the formula for the linear approximation in general, okay, this right here is really your A value in the formula. Okay, so the formula says you would do the f of A plus the f prime of A times x minus A. Okay, and so f of A really means f of 1, f prime of 1, and then x minus 1. And f of 1 would be square root of 1. F prime of 1 would first involve you getting the first derivative, which equals 1 over 2 square root of x. Okay, and then f prime of 1 would be plugging in a 1. Okay, and then multiplying that by x minus 1. Okay, so square root of 1 is 1. This turns out to be 1/2. This turns out to be x minus 1. We distribute, collect like terms, and we wind up with it being 1/2 plus let's see, where I'm kind of lost here where I got to. Okay, so it's 1/2 plus x over, yeah, so this is 1/2, and then I have plus x over 2. Okay. All right, now that is the equation, basically, of the tangent line to the curve right here at that spot where x was 1. So if you're trying to approximate what f of 1.1 is without using the function, without using the calculator, so this is usually on one where it's maybe kind of complicated. Since you're just moving a smidgen away from the point you just used, it's just 0.1 away, then this would be a good approximation. And so if you want to know then how to use it to approximate the square root of 1.1, what you're going to do is just find L of 1.1. So it'd be 1/2 plus 1.1 over 2. Okay, or you could have factored out the 1/2 like they did if you wanted to, and write it as 1 plus x or x plus 1, either way. So you do 1/2 plus the 1.1 divided by 2, and you wind up with 1.05. Okay, so what we're claiming then is that the square root of 1.1 is about 1.05. Okay, now you can do that on your calculator directly though, can't you? So if you do the square root of 1.1, you see that the actual square root of 1.1 on the calculator, so this is using L of x. But if I use the calculator, what I get is that the square root of 1.1 turns out to be 1.40488009. You know, I just carried it a little bit further, and you see it's a good approximation, isn't it? And see, sometimes using a line is just way easier than using the original function. So that's why we sometimes like to do this. And as long as we just moved, like the difference between where we were and where we are now was only 0.1 away, so we're close to that spot right there, then that means you're going to have a good approximation. But like, look, if we use it to estimate the value of 0.1, which is way over here, watch what happens. We use the linear approximation to do this. We're going to be putting 0.1 in, so we'd have 1/2 plus 0.1 over 2, and that would wind up equaling 0.55. But then when we use our calculator and do this, we get a quite a bit different. We're pretty far away from that point of tangency. Do you see how we're pretty far away from it? See the difference? This would be the difference between what we'll get using this function and what we'd get using the original function. See, I got 0.3162, if I carry a lot of accuracy. So quite a bit different. So this is a bad approximation. And it's bad because we're far away from that point of tangency. Okay. To improve things, what we should do is maybe move and redo the linear approximation so that we're closer to that. So maybe instead of being here, create a new linear formula for the linear approximation and maybe be like right next to it, like 0.2 or at 0.9, something closer. Okay, so that's the idea behind linear approximation is sometimes your original function is quite messy, but anything is basically linear if you zoom in enough at a spot. And so you can use the equation of the tangent line at a spot as a good approximation for the value of the original function as long as you're near that point of tangency. Okay. All right, so now let's look at some of the homework you might see because it goes a little bit further. It starts asking you also to quantify the error. Okay, so what that's getting at is when you look at this picture, let me get rid of the stuff I wrote on it so you can see it better. When we wind up using our calculator to find the value of that function at 0.1, it would be there. It would be right there, okay? When we use the linear approximation to get the value of the function, we're actually finding this, which is quite a bit higher. That's 0.55. This right here is the 0.32. So what we've got to do in part C is quantify that error. Like how bad of an approximation is that? So that's the extra little piece we're going to do on these. Okay. All right, so I thought we'd do two of them. Why don't we do 25 and 27, the odd ones? Okay, so on 25, part A says, write the equation of the line that represents the linear approximation to the following function at the given point A. Okay, so you got your formula. So you know the linear approximation equals f of A plus the slope times x minus A. All right, we know that A is 1. No, A is 2. Okay. We can get the derivative of the function in general. So let me do that. So the derivative of 12 is 0. The derivative of negative x squared is negative 2x. And then the value of that at 2 would be negative 4. So f of 2 we need to find as well. So let me do that. F of 2. I'm going to go to the original function and plug in 2. So that would equal 12 minus 2 squared, which is 12 minus 4, which is 8. So now I have, I think, all the pieces that I need. So f of 2 was 8. F prime of 2 was negative 4. And then x minus 2 here. And this is really just plus a negative, so you can just say 8 minus that. Let's go ahead and distribute. So that would be 8 minus 4x plus 8. So that would be 16 minus 4x, or negative 4x plus 16. This is a linear approximation. That's why these are turning out to be lines. So this function right here is supposed to be an estimate of the original function as long as you're right around 2. It should give you a close estimate. Okay. All right, so now that's the end of A. Now B says, okay, well, use that estimate, use that approximation to estimate the quantity they're asking you for. Okay. All right. So what we got to do for part B. So all that work that I did, that's all part A. Okay. So with part B, I've got to actually find an approximation for f of 2.1 using this. So I'm going to do L of 2.1 and get that worked out. So that's 16 minus 4 times 2.1, and I get 7.6, and that's an actual equal sign because I'm really finding the value of the linear approximation. So it equals 7.6. Okay. The thing is, that's not what f of 2.1 would really truly be. Now, sometimes your function is way harder than this one, but on this one, what they're asking us to do is get what the actual value should be. So that's when you would actually plug in 2.1 into the function itself that you had to start with and just use your calculator. So if you didn't have ready access to a calculator, the linear approximation would give you a quick estimate of the value of that. Let me get this back up here. So we got 7.59 when we did it actually. Okay, so that's part B. Part C says, tell us the percent error. How far off were we? Okay, so that's when you take your approximation and you subtract the exact value, what it was supposed to be, and you divide by the exact value. Okay. And I usually just do that to start with, and I don't put the 100 in there. I just get this, and then I convert it to a percent. So you're just doing the percent change, really. Okay, so you know how that would be 0.01 over this. And when you divide that by 7.59, because you're trying to find out how big of an error was it, you compare it back to the original, and you get 0.001318 if I rounded to that spot. Let me say approximately since I rounded. And then it wanted the percent error. So I'm going to change that to a percent. Okay. So that's why in the formula, you could do it in the formula to start with. That's what the 100 was. Absolute value means they don't really care whether it's an underestimate or an overestimate. So you can do the absolute value of it. But that's the reason for the 100 is you're actually converting it to a percent. So it's this about 0.13% of an error. Okay. And so, if you were in manufacturing or something, that might be intolerable. You have to watch it. Sometimes you have to calculate your percent error to see what you can live with. What's too much of an error. Okay. All right, so let's do another one so you get the hang of it. So basically, you're going to start with a function like on 27. Let's do 27. I like to do the ones that you have less experience with, like logs or trig functions. We're given the function, we're given the a value, and we're being asked to find 0.9. Okay, I'm already suspicious of this because the point where we're going to find the tangent line is way back at 0. But then what we're trying to actually find is 0.9. That's almost a whole unit away. Where, see, on this one, the a value was 2. This equation we got was the equation of the tangent line at that a equal 2. And we were only 0.1 away. So notice the error was just 0.13%, not 13%, 0.13. Okay. All right, so what you got a lot of different things you got to do, but the formula you're trying to get is this. So f of a plus f prime of a times the quantity x minus a. All right, so we got to get a few pieces of information to be able to plug into that. First off, a is 0, okay? So we're going to really need to do f of 0 and f prime of 0, and then it's x minus 0, which is just x. So f of 0 would equal the natural log of 1 plus 0, which equals the natural log of 1. You can do that on your calculator. It's going to be 0. Natural log looks like this, and it's going to have a 0 when you're at 1 on the x-axis. Okay? All right, then I'm going to need to find the derivative of f in general first, which would be derivative of natural log is 1 over. And then you got to do the derivative of the inside, but the derivative of the inside is just 1. Okay, so f prime of x, that's the formula for the derivative. Now I need f prime of 0. So it's like over here is my scratch work. Okay, so it's 1 over 1 plus 0, which is 1 over 1 or 1. We got what we need. We'll come over here. F of 0 is 0. F prime of 0 was 1. And so when I simplify this, I get 0 plus just x. So that's really going to be x. Now see, this is really good. It's saying that you can use the linear approximation, the line y equal x, to estimate the value of the natural log of something. Okay. So this y equal x is going to be a approximation for the value of the actual function f. And this right here is just the tangent line to the curve at 0. But we're being asked to find f of 0.9. So let's see what happens when we put that 0.9 in here. We get 0.9, don't we? Okay. Well, what happens when you use the original function to find it? Find it exactly find it using the original function. Use your calculator. What do you get? I don't think I plugged in. Let me see, where was it? Oh, yeah. Okay. Okay, so what is ln of 1.9? Okay. So when I do that, I get about 0.642. Okay. All right, so there's a considerable difference there. So what I'm being asked to do in part C is to compare those. So take your approximation minus what you got when you used your calculator over what you got when you used your calculator. Okay, you don't care whether it's positive or negative. And if you want to go ahead and let the formula determine the percent multiplied by 100, otherwise get the value of that inside part and then change it into a percent. All right, so let's see what that winds up being. So really, I just don't like doing that part. So I'm just going to do the 0.9 minus the 0.642, hit enter, then divide by 0.642, and I get on that, I get about 0.402. Wow. When I change that into a percent, that would be 40.2%. So remember to change it into a percent, you move the decimal 2 places and add the percent sign. Okay. So a 40% error we got there. On the other one, we had a 0.13%, less than 1% error. The reason this error was so humongous was because here was where I wrote the equation of the tangent line, but then I'm looking for the value of the function way out here, okay? And so I'll show you what it kind of looks like. So ln of x, let's see, that's been shifted to the left one, is going to look something like this, okay? And so if you look at the tangent line, when you're out at 0.9, do that in black, okay? Yeah, that's okay. Out somewhere like at 0.9, almost to 1, here's your tangent line, okay? That's not what I meant to do. I want my tangent line to be here. Here's my tangent line. Basically, that tangent line is y equals x. I'm trying to estimate the actual value of the function out here. So do you see how there's a lot of difference between what you would get using the regular function and what you would get using the linear approximation? The amount of this change turns out to be 40.2% of the original value. So bad approximation. You shouldn't have done it. You should have done the equation of the tangent line maybe at 1 and then gone to 0.9, done the linear approximation at 0.9. So if it was up to you to choose what you should do to get a good approximation, it should have been maybe using, instead of a equaling 0, have a equaling 1. Would be better. Okay. All right, but that's how you do it. And that's mainly all I want you to understand. All right. Now let's continue on and look at this image and see if you get the idea here. All right, there's a concept here I want you to understand. Just kind of get the gist of a little bit. All right, so this really comes out of, this is talking about this change in x and change in y. That's like the y2 minus y1 from your slope days and the x2 minus x1 from your earlier time period. Okay, and it's just change in x and change in y is what we use for that. So if you have a differentiable function on some interval that contains the point you're looking at, the change in the value of the function between these 2 points can be estimated by using this formula. Okay. It's just pretty much a restatement of that earlier formula. Remember the earlier formula that looked like this? Okay. All right, what they said, what they're doing to get this right here is they're saying, well, L of x is basically f of x. It's not really, though, because remember, this might be your function, and this was the tangent line. This is L of x. This is f of x. So they're really not equal, but as long as you're close to this, they're approximately equal. So this formula, L of x is approximately f of x. So that means f of x would be approximately this. I'm just replacing L of x with f of x, but now it's approximately that. Okay, and then they subtracted the f of a from both sides, then you would still have that. Okay, and then f of x minus f of a would be like, would be kind of, well, kind of hard to say exactly what I want to say, so let me not try to do that. But it's that right there would be the change in the y's, and that would approximately equal f prime of a, and then x minus a is just the change in the x's. Okay, that's where the formula came from. Something else that comes out of linear approximations is that idea. All right, so there's a better picture here that might maybe or maybe not might help. Okay, just make it bigger. All right, so you got your original function. This red line is the equation of the tangent line to the curve at A. You're actually trying to estimate something that happened out here using the linear approximation. But see, if you're at A and you move some quantity away from it to this new point X, okay, then this is the change in the X's. And if you do that, then here you are at f of X, and f of A would have been down here. And so from there to there is the actual change from f of X to f of A. But you're not using the original function. You're using the linear approximation. So it's really just this amount right here. But it'll be close to this as long as these are close. So if A and X are close, then these are going to be close. This right here and this right here. Then these are close or approximately equal. Okay? So here's the kind of problem that you could do as a result of that. It says, approximate the change in y, the function defined by the x to the 9th minus 2x plus 1, when you change x from 1 to 1.05. So if you go from 1 to 1.05, estimate what the function change is, but use the linear approximation to do it. Okay. All right, so you're going to start on A by thinking about the formula that we just wrote down, that the change in y is estimated by using this formula. Okay. All right, your A would have been on this one, your A value would have been your starting point. Okay. The change in X would be that change in X would be that distance from 1 to 1.05. So it'd be this difference. Okay. And then you know how to do first derivative. So we're going to need the first derivative. Let me do it right up here because I like it underneath that. That'd be 9x to the 8th minus 2. So if I need f prime of A, I need f prime of 1. I just plug in a 1 into that. And that's going to be 9 times 1 minus 2, which is 7. Okay. So I'm trying to estimate the change in y. I'm going to do it by doing f prime of 1 times the change in x when I go from 1 to 1.05, which is times 0.05. So it's going to be 7 times 0.05, which would be about, let's see, that would be 35, so that would be about 0.35. So when x changes from 1 to 1.05, this right here is what's really, this is really 0.35, but we're using it to estimate that. We're using it to estimate the vertical change in your actual y coordinates. So that's A. Okay. All right, so on B, I'm going to use the same formula. Okay, it's not related to part A. It says approximate the change in the surface area of a spherical hot air balloon when the radius decreases from 4 to 3.9. Okay. So A is 4 because it's your starting point. So A is the starting point, and then you're thinking about what you're moving to. So here you would let A equal 4. Okay. Then change in X would actually be the 3.9 minus the 4, and it turns out to be a negative 0.1. See, this time the radius is decreasing, so that's why that's the change in X is a negative 0.1. Okay. All right, then the surface area, you have to know that. So if you didn't know it, you would look it up. And the surface area turns out to be, they usually use S, but since I was using Y's, I'm just going to use Y. Surface area is going to be 4 pi r squared. Okay, so surface area of a sphere, area of a sphere would be the formula 4 pi r squared. We're dealing with area, not volume. Okay. All right, so what I got to do for the formula is I need to know f prime at a, so f prime at 4, and f prime means I have to take the derivative here. So wouldn't the derivative be 8 pi r? Remember, pi is not a variable. Okay. And so if I need to know the value of that at an a value of 4, I would plug 4 in there, and that would equal 32 pi. Okay. All right, so I'm gonna get, plugging into here now, into here now. I know then that the change in y is approximately equal to 32 pi times the change in x, which was negative 0.1. So the change in y is approximately negative 3.2 pi. Okay, and that's about negative 10.05, and that would be meters squared. So as the radius decreases from 4 to 3.9, the surface area of the balloon decreases by 10.05 square meters, about. Okay. All right, so this box just kind of summarizes those two rules. It's the same rule, it's just they rearranged in order to get your to get this one. We brought the f of a over here, okay, which was really the change in the y's, and then we called this change in x. So these are just equivalent statements, just written in different ways. All right, and then one last thing I want to mention is the idea of a differential. All right, so that change in y that we keep talking about can be approximated by d of y. One of them is like using the linear approximation to the curve, and then the other one is the actual change in the y's. Okay, so let's just read this to start with. So f has to be differentiable on an interval containing x, and this says a small change in x is denoted by the differential d of x. It's pretty much delta x in a way. The difference is whether you're on the actual function or on the linear approximation. The corresponding change in f is approximated by the differential dy equals f prime of x dx. So that looks a lot like this, doesn't it? Except for with a dy in there. See that? Okay. So what it's saying is the change in y, the actual change in y, can be approximated by using this formula right here. Now, I kind of remember it. I don't know if this is really like technically correct, but dy dx was just another way to state f prime of x. And so see, if I multiplied both sides by dx, I would get that formula. Because the dx would cancel out. So that's another way to kind of think about it. But you won't have to memorize these. You'll just have the formulas and just have to see the problems that you're going to do. Okay. All right. So like dy and the dx go with the linear approximation to the curve, where change in y and change of x deals with the original function, but they can be used to approximate one another. Okay. All right, so let's see what they're going to ask us to do. So on example 6, it says, use the notation of differentials to write the approximate change in f of x equals 3 cosine squared x given a small change dx. So you basically go and you come up here and you take that formula and you say dy would equal f prime of x dx. So you're going to take this and do the first derivative. So f prime of x, wouldn't that be negative 3 sine squared x, because the derivative of cosine is negative sine, but then you got to do the derivative. Oh, wait, let me do that. I did it in the, let me do that better. Okay. Eventually I would have gotten there, but let me do it better. Think of this as 3 cosine x squared is the best way to look at it. So to do the derivative of that, I'm going to bring the 2 down in front, okay, times the cosine x to the first. Then I'm going to do the derivative of the inside, which is negative sine x. Okay, so what I'd really have is a negative 6 sine x cosine x. So when I come back over here and plug it in, d sub y would equal negative 6 sine x cosine x dx. Okay, times that dx. And look, there's a whole, like, I took a whole class that was just differential equations. Differential equations. And this is just a brief look at the idea of a differential. Okay. All right, and then sometimes on trig ones, what gets us into trouble is what you put in might have been simplified to be something else, and then you may not have used an identity or something. So I would have taken that answer. But one of the common identities is that sine 2x is the same as 2 sine x cosine x. So we really could think of this as being negative 3 times 2 sine x cosine x dx. And this is really sine 2x. Okay, so that would be also correct if you used an identity to get there. Okay. But I don't think that would make me want to count that one wrong. All right, so these almost seem kind of pointless because there's not really a lot of work you do. So let's look at 63. Okay, f of x is 1 over x to the third. I'm trying to use this formula and express a relationship between a small change in x and the corresponding change in y in that form. So d sub y equals f prime x dx. So I'm going to do f prime of x, and when I do, I like to think of that as x to the negative 3. It makes it a little easier. So it's negative 3x subtract 1 would give you negative 4. So it's negative 3 over x to the 4th. So when I use the formula, that goes there. We keep the dx on it, and that's dy. That's expressing the change in y in terms of that small change in x, and that would be your final answer. Okay. All right, let's do one more. Let's do like 64. All right, so on 64, we have the function given to us. It's e to the 2x. I want to express the relationship between the small change in x and the corresponding change in y. It equals f prime of x dx. So I basically take the e to the 2x function and I do its derivative. Well, the derivative of an e function is the same thing, but you have to take the derivative of the inside. So you get 2e to the 2x. Then all you're going to do is put that where f prime of x is. And there you have it. Okay, so this last unit were some other things, some other applications of derivatives that I wanted you to be exposed to. Okay, so I'm going to stop this and get it posted in that same homework so you can look at it. And then there'll be a take-home assignment, which is basically to write up selected problems off of the homework that you're doing and turn it in for me to grade in depth. Okay, so let me stop